Hey there, science fans. Have you ever wondered how electricity flows through wires and powers our devices? Let's dive in and explore the fascinating world of charged particles on the move. At the heart of electricity are tiny particles called electrons. These electrons carry a negative charge. When electrons move in a specific direction, we get an electric current. Think of it like a river, where the water molecules are like electrons flowing downstream. Materials that allow electrons to flow easily are called conductors. Metals, like copper, are excellent conductors because they have loosely bound electrons that can move freely. That's why we use copper wires to carry electricity. On the other hand, insulators are materials that resist the flow of electrons. They hold onto their electrons tightly, making it difficult for them to move. Examples of insulators include rubber, glass, and plastic. That's why electrical wires are coated in rubber or plastic to keep the electricity flowing safely inside. Now that we know how charged particles move, let's talk about what makes them move in the first place. Just like a pump is needed to push water through pipes, we need something to push those electrons through a circuit. That's where electromotive force, or EMF, comes in. EMF is the energy provided by a source like a battery to drive the flow of charge. It's measured in volts, named after the Italian physicist Alessandro Volta. You can think of EMF as the electrical pressure that pushes electrons through a circuit. The higher the voltage, the greater the force pushing the electrons, and the greater the current flow. Just like a higher water pressure will make water flow faster through a hose, a higher voltage will make electrons flow faster through a wire. Where does this EMF come from? Well, we can get it from various sources, but one of the most common is a cell, like the batteries we use every day. Cells store chemical energy and convert it into electrical energy, providing the EMF needed to power our devices. Imagine a chemical cell like a tiny factory. Inside, chemical reactions occur, releasing energy that pushes electrons from the negative terminal of the cell to the positive terminal. This creates the electrical potential difference or voltage that drives the current. There are different types of cells, such as chemical cells like the batteries in your remote, and solar cells, which convert light energy into electrical energy. No matter the type, they all work by creating an EMF that drives the flow of charge. Section 4. Mapping the path, decoding circuit diagrams. To understand how electricity flows in different setups, we use circuit diagrams. These diagrams use symbols to represent different components, making it easy to visualize the flow of current. Let's break down some common symbols. A cell is represented by two parallel lines, one longer than the other. The longer line represents the positive terminal, and the shorter line represents the negative terminal. A battery, which is just a combination of multiple cells, is represented by multiple cell symbols connected. A switch, which can open or close a circuit, is represented by a line with a gap that can be closed or opened. A resistor, which resists the flow of current, is represented by a zigzag line. A light bulb, which converts electrical energy into light, is represented by a circle with a cross inside. By connecting these symbols with lines representing wires, we can create a visual representation of how electricity flows in a circuit. For example, a simple circuit with a battery, a switch, and a light bulb would show the current flowing from the battery, through the switch to the light bulb, and then back to the battery. Section 5. Current affairs, direct current and charge flow. Now that we know how to visualize circuits, let's talk more about the flow of charge, also known as electric current. Direct current, or DC, is the flow of electric charge in one direction. It's the type of current we get from batteries and solar cells. We measure electric current in amperes, or amps, named after the French physicist André-Marie Ampère. 1 ampere is equal to 1 coulomb of charge passing a point in a circuit per second. Think of it like measuring the amount of water flowing through a pipe per second. The more water flowing, the higher the current. We can express the relationship between current, charge, and time with a simple formula, I equals dq divided by dt. This formula tells us that the current is equal to the amount of charge flowing past a point divided by the time it takes for that charge to flow.